So, demonstration of diffraction using ripple tank. It's like this. So if you consider, right, if you consider the ripple tank, so basically, right, okay, before we move on to ripple tank, we need to see refraction of like what happens, like how, okay, we are going to, we need to see speed of water waves. We need to see about the speed of water waves, because refraction is going to depend on the speed of water waves, right? Because simply we are going to demonstrate refraction using water waves. So refraction occurs due to change in the velocity of water waves. So first of all, we need to analyze the speed of water waves. How it's going to look like. Yeah. For example, let's see in this way. Let's consider a seabed, right? And this is sea. This is the water body. All right. So this is the land, right? This is how the depth varies. So here it's very depth. So here it's shallow. So you need to understand that. Right? You need to understand that when this is how water waves are going to propagate. We will be discussing about water waves, the speed of water waves in detail later. For the time being, only the required things are going to be discussed, right? Even the tsunami took place based on this concept. Concept means we can explain the tsunami waves also based on the physics behind this. Obviously you might have seen in beach area, like in sea, when you look at a wave far at the horizon, waves do start with very small amplitudes, and when it comes closer to the beach, the amplitude of the wave increases. Amplitude of the wave increases. That is because the speed of the wave can be written as root GH. How did I get this? That doesn't matter. Like that doesn't matter, and you are not required to prove these things. It's given. The speed of water waves can be written as root GH. Very important. Root GH. When height varies, velocity varies. When the height, So at the seabed, velocity of sound waves, sorry, velocity of water waves has a very high velocity. Why? Because it has a large depth. When it reaches the shore, the velocity of the waves decreases. Velocity of the wave decreases. When the velocity of the wave decreases, when you come towards the shore, the height decreases. As a result, velocity decreases. Velocity decreases. As a result, what should happen? The wavelength should decrease. The wavelength should decrease. When wavelength decreases at the depth, at the very depth, this is how the wavelength is going to be. This much of flow, just for you to demonstrate. At the same energy at the shore, the wavelength should decrease due to decrease of velocity. Right? Height decreases at the shore, velocity should decrease. If velocity decreases, lambda should decrease. If lambda is supposed to decrease, it should contract. This is why large waves forms at the shore, right? Simply, there was a question once, a passage question, a paragraph question actually, relating the tsunami waves and this equation. They ask how will you explain the large waves formed in tsunami, in a tsunami wave or something, very close to that, right? So this is pretty much it. This is how you explain that. Right? So they gave you in the passage they gave the this thing also, equation also. Simply at the depth, at deep sea, height is large, velocity is very high. When velocity is very high, according to V equals F lambda, lambda is very high. At shore, the depth is very low, velocity is very low. When velocity is very low, lambda is very low. When lambda gets shorter, amplitudes rises, and due to this, large waves are formed. Right? This is a basic story. Right? So I guess you can relate this to tsunami. Now, we are talking about tsunami, right? So, demonstration of refraction is a ripple dance. To demonstrate that, the equation that we have is this. These things I just gave you as an additional knowledge, right, for you to relate, for you to make you feel like this equation is true, because usually we derive equations, but in this case, in your syllabus, it's not supposed to be derived, right? So therefore, like, you need to feel some confidence on that equation for you to remember. You just can't buy hard things, right? Now you can, based on the story that I told, now you can maybe have an idea. It shows that kind of, it shows that this is true, it seems. Right? Anyways, right? Okay, that's fine. So D is equal to root GH. So now we need to demonstrate refraction using ripple tank. Okay, so I will use a ripple tank. I will use a ripple tank, right? Just give me a sec, guys. Now, how will you? Okay, so for you to show refraction, there should be two mediums, but it's just one medium, water. Only one medium. You can't. If you need to make two mediums, you need to separate this by another. Are you going to separate by placing a osmosis layer or something, and then like are you going to add some other liquid on the other side? You can't do that, right? You can't do that. You just have to somehow. You just have to do a small trick. If you understood this theory part well, you will now, it will have flashed straight away the trick. We're going to do a small trick. Obviously, there's no two regions. Obviously, there's no two regions. So, guys, this refraction occurs in the first place. Why? Because in two different mediums, the velocity of the wave changes. So, if we can trick the wave, if we can change the velocity of the wave, we can make the wave to feel like there are two different mediums. If we can change the velocity of the water wave, we can make the water wave feel like it's two different mediums, and because if that water wave feels that it's two different mediums, it will refract. To do that, what we do is we place a cube. A cube. We place a cube. Right? We place a cube, and what we do is we change the height. Initially, the height was this. Now, the height is this H2. So now, if we oscillate in this region, a water wave will start to propagate. When this enters this region, what happens is the velocity changes. The velocity changes. When it enters this is considered as medium 2. This is medium 1. How did I do that? This is medium 1 and this is medium 2. Obviously, according to V is equal to root GH, V is directly proportional to root H. In this medium, the height is H1. When the height is H1, the wave is going to have a velocity V1. Medium 2, the height is H2. Height has changed. Therefore, the velocity will also change. The velocity will also change. So simply, If the velocity changes, what happens? A refraction will take place. A refraction will take place. This is what? A glass cube, right? A glass cube. A refraction will take place. All right. Simply, we just stripped it, right? Okay. So now we'll see how the wave is going to look like. Right? Wave. I will draw the top view. I will draw the top view of the ripple tank. I will draw the top view of the screen. Frequency doesn't change. So who is the one who is deciding the frequency? This guy, oscillator. He is the one who is deciding the frequency. Right? He is the one who is deciding the frequency. So the frequency doesn't change. Right. What happens is, if this is a planar vibrator, right? It will, like, let's like kind of turn this somewhat, right? Let's kind of incline this and place it on the ripple tank. The cube, it's kind of incline it and keep it inside, right? So in that case, this is the cube now. This is the cubic region. This is the region where the cube is. This is medium 1, this is medium 2. Medium 1, medium 2. So if you propagate using if you vibrate using a plane rod, planar waves are going to, planar wave fronts are going to move. Planar wave fronts. Planar wave fronts. So this is the surface. So what will be the normal? This will be the normal. So now this thing you need to understand it, right? So when demonstrating using the ripple tank, this concept you need to understand it. Questions are going to be there. So who is the denser medium? Who is the rare medium? They will ask that. Definitely they will ask that. So who is the denser medium? Who is the rare medium? Medium 1, medium 2 is there. Okay. So who is the rare medium? Who is the denser medium? Water wave is a transverse wave, right? Water wave is a transverse wave, right? So when you consider transverse waves, when it moves from a dense rare medium to denser medium, its velocity decreases. Inside a rare medium, a transverse wave is going to have a higher velocity. Inside a rare medium, velocity is high. Inside a denser medium, velocity of water waves is low, right? So what can you say about the velocities V1 and V2? Who is higher and who is lower? How will you decide that? Velocity is directly proportional to the height. Velocity of with a wave is directly proportional to the depth. So in this, the height is higher. H1 is greater than H2. Therefore, V1 should be greater than V2. V1 is greater than V2. So the medium which has the higher velocity is rare. Medium which has the higher velocity is rare. Medium which has the lower velocity is denser. So this is rare. This is denser. It's rare. This is denser. Alright. Okay. So now what happens? Rare to denser. Now actually what happens is actually this is what happens. This is not how you start to draw, right? Sorry. This is not how you start to draw the refracted wavefronts. So this is the normal. This is the incident ray. When the incident ray moves from rare to denser, it will deflect towards the normal. It will deflect towards the normal. Right? Therefore, the incident, therefore the refracted wavefronts will be perpendicular to this wave. It's going to move in this way. Velocity high, velocity low. What about lambda? When velocity is higher, according to V equal F lambda, V is directly proportional to lambda. When velocity is higher, lambda also higher. So in this, lambda is higher. Here, lambda 2 is lower. You need to definitely draw in this way. If not, 100% it's incorrect. They will mark it as wrong. If you have everything marked properly, but the distance between these wavefronts, if this distance is greater than this distance, it's wrong. A lot of things are there to consider when you consider refractive, the demonstration of refraction. A lot of things are there. Okay? So very important. Okay, so this is lambda 1, this is lambda 2. Lambda 1 is greater than lambda 2. When region changes, height decreases. When height decreases, velocity decreases. When velocity decreases, lambda decreases. When lambda decreases, the wavelengths, they are somewhat closer to each other. Pretty simple. Right? Pretty simple. So, and also, there is a certain thing that you need to, there is a certain condition. There is a certain condition where there is a certain condition it should satisfy. There is a certain condition that it should satisfy for you to use this V equal root GH equation. Condition to use equal root GH. V equals root GH can only be used when the wavelength is higher than lambda, the wavelength is greater than this height. When this height is greater than the lambda value, less than the lambda value. This is the lambda value. This height should be less than this lambda value and should be greater than the amplitude. Should be greater than the amplitude, right? This is the condition. The height to the depth should be less than the wavelength, and this height should be greater than amplitude. Definitely, they might ask this also. What are the conditions that the height should satisfy for you to apply V equals root GH equation? This condition, right? Height should be less than the wavelength, height should be greater than the amplitude, right? So this is it for the demonstration of the wavelengths, the refraction.